Bigger than here today. It's pretty weird. Oh, she did. Oh, okay. All right, that's good. Oh, wow. She was here. So, yeah. Anyway, I was going to there were like anyway, I've been going with like last year's homeworks, but then this it seems like we haven't finished this phase diagram thing, so I got a new homework that's on ternary phase diagrams. So anyway, so it's kind of like I'm not sure why last year I was ahead. I think I just skipped some of this stuff last year, maybe. I don't know what. Anyway, I wanted to just finish this. It seemed like there was enough to do today, almost on this on phase diagrams, and then start this next section. It's like stability, which ends up being like a bunch of different things thrown together. But spinel decomposition is one of the things. So there's a homework on that for maybe a week after. You know, so anyway. So I went through this eutectic thing. So that's just, it's like if you like if people ask you questions from material science, they expect you to know this phase diagram. So you should be able to draw the eutectic phase diagram, basically what's shown here. Anyway, I'm not sure, other than saying that, I'm not sure how to emphasize that, but that seems to be like the main thing people expect. Anyway, then you can calculate that. I mean, I started to go through how to calculate phase diagrams using the Hildebrandt function. But you can, so the software that uses the Hildebrandt to do that, so it used to be two separate softwares. ThermoCalc was a Mac software, and this CalFAD was a PC software in Linux. But now I guess anyway. So if you click this, there's a link that goes to see it's thermocalc.com. So I think like ThermoCalc might have purchased CalFAD, even though CalFAD was the main thing. So you can download a free ThermoCalc on a Mac and CalFAD on a PC, but basically it's all called ThermoCalc now. And then you can do things like this is the standard one, like solder. So it's like copper and lead, I guess, mixture, and then it ends up being eutectic. You can put in the temperature range you want to look at, composition range. This is a fairly simple phase diagram. For more complicated ones, sometimes you just blow up a region, like for the steel for the iron carbon, which is steel, then you just blow up the part that's like 2% carbon, and that's basically how you make steel, like carbon to iron. So anyway, and that has a lot of different phases, like in the low composition range. So you can only plot like to 5%. You see a lot there where you could manipulate how to make steel through these quench processes and things. Anyway, so that's there if you want to mess around with it. So it's anyway, just mention that, I guess, but it's not for polymers, it's for only for ceramics and metals. So just low molecular weight things. Went through a little bit of the eutectic stuff. We already went through different kind of how you use a phase diagram to do kinetic studies. I wonder if something else is going on today. Maybe I'm missing something. I always like sometimes there's some kind of thing, but anyway.
Grad stuff because I only sometimes get emails about it.
Yeah. I got an email today about like a Halloween party, but it was going to be held on Teams. It was kind of weird looking. It's like, what would you do? Like dress up for the video? Only dress up your top half, Yeah. I mean, anyway, yeah, and it was like a 4-hour Halloween party on Teams. I don't know what. Anyway, people do things. So I went through this. How to basically each one's a Hildebrandt, and then you can kind of map out the chemical potentials where the slope of the free energy curve gives you the chemical potential, and if two have the same chemical potential, two people, good. Right. So if two have the same chemical potential, you map out those points on a temperature composition, and you can make the phase diagram. So if you have the Hildebrand equation, you can get the phase diagram. And then if you want to just calculate the phase diagram, you figure out how to calculate the chemical potential, which from the free energy, so this is the molar free energy, so dg dn is the chemical potential. So from the square, you have dg is s minus sdt plus vdp. If you go isobaric, vdp, if you go isobaric, or no, you go isothermal, and then you have, for ideal gas, V's RT over P. So then you have dP over P. If you integrate, you get ln of P, and you have with that term, which ends up being that ln of the activity. Right. So you have this expression that chemical potential is ln of the activity. So if you have ln of the activity, you can calculate the chemical potentials. If you have two phases that are equal, then it's just going to be using the chemical. So like we have a liquid and a solid solution in equilibria. When you have chemical potential of the solid and the activity of the solid solution, and basically, or you could say that if it's ideal, the activity is mole fraction x. So then you can just work that out to get equations that relate. You have two equations for each of the components, like the A for a binary mixture, A component, B component, liquid solid solution, liquid solid solution. Then you have two unknowns, which will be like, so XA plus XB gives 1, XA plus XB gives 1 for the liquid and the solid solution. So basically, you only have two unknowns in this, and you have two equations. You can solve that. You can solve those two equations. And we figured out how to use the heat of fusion for the chemical potential thing. So basically, if you know the heat of fusion, you know the melting point, you get the equilibrium compositions, then you can construct the phase diagram as a function of temperature. So I went through that last time. I guess it's in the book. This is all basically in the book. So you can kind of, that's how these things can be constructed in a program like the CalFAD program. Like that's basically what it's doing, this thing. So again, like you can download that if you want. I gave a homework before to do this. Like you just, let's see. Here, you just fill this out and they give you a copy of it. But it's a big program. Like it takes up like, I think it's like 100 megabyte. It's pretty big. And I think compiling it and stuff is a little bit of a problem. But once you have it, it's just a pull down menu that you can calculate any phase diagram you want. So anyway, that's based on this exactly like this kind of calculation, except this is assuming that the heat capacity there's no heat capacity contribution. So you're going to so you have the heat of fusion and the enthalpy of fusion. So the enthalpy of fusion goes with the heat of fusion. In other words, it's melting at a certain temperature, like 0 degrees C for water, and then the heat of fusion is at that temperature, right? But in reality, and then you're going to another temperature where you need to take the material from the heat of fusion to that temperature with the heat capacity. So it's going to be like integral of Cp dt is going to give you the enthalpy, and integral of Cp by T dt is going to give you the entropy. So if you ignore the heat capacity thing, you get the black lines. If you include the heat capacity, you get the dashed line. So it shifts the result of this thing. Like CalFAD will be using heat capacity. So when you do that, you get like this equation. So you're going to have like the heat capacity integral to go from heat of fusion, where the delta H is, to the temperature where you're looking at to calculate the phase diagram. So you have this term, and that the heat capacity itself is a temperature dependent function. Okay, so this is where you go to like the NIST web book. It has the heat capacities of everything written in this form, like A plus B, and then small t is actually temperature here in that time. So I'm not sure why they use small t, but So this is a 4 or 5 term equation, kind of a polynomial that describes the behavior of heat capacity. And they give the ABCD for everything on Earth, every kind of material. So then once you have that, so if you integrate that dt, you end up with, well, the A term drops out, you have B, or no, A becomes A times T, T minus T fusion. So you can figure out how to integrate that. And then you plug it in. This is what CalFat does. Or you can do it yourself in Excel or something if you want. And then the same with this, except you divide by T first. So the T, so you get a little bit different answer from the integral. But basically, these two become analytic functions. So you can just calculate the chemical potential of the two phases and solve for the compositions on the phase diagram. So it gets a little bit more complicated than that. It's like you have to do this heat capacity thing. But again, like you can do this yourself, like if you want. But I gave a homework on this a while ago, and it was kind of like easy. It was just like calculate some things. It was like an undergrad homework. So I didn't think it was that valuable for grad students because you're beyond this at this point. You're not going to do this probably. I mean, if you were writing the CalFad program, it's like you got a job after working for Thermocalc to write the CalFad program, then yeah, you would do this. But I think everyone in here can do integration and that calculations kind of like basics. So I don't know, it's a little goofy to give you that for homework. If you want, you can, I think that the best thing would be to go to the CalFat and play around with it and try to make phase diagrams if you want to mess around with this, if you're interested in it, but otherwise, just know that someone says on a paper they got the phase diagram from CalFad, kind of roughly where it came from. That's probably good enough. And if you actually need to do it, you can go back and figure it out, I think. But, so there's these simple solid solutions where the two crystals, so germanium and silicon, both are diamond cubic, they're roughly the same size, they fit in the same lattice, roughly. So they're completely miscible over the whole range with the same crystal structure. So lattice constant A will shift as you go across composition, but basically it's the same crystal, so it's the same phase that's in equilibrium with the melt of these two semiconductors. And so they form this kind of solid solution phase diagram. So you can also have conditions where either the liquid is stabilized compared to the solid solution. So in other words, this is really like an ideal. So for the two Helmholtz equations, they're really ideal mixing. They don't have, like, when you get the solid solution like this, there's no interaction enthalpy between the germanium and silicon. They have the same, they can't distinguish between each other. Right, so you get a solid solution curve like this. If they can distinguish between each other, then you have either they attract each other or repel each other. And then the liquid phase can also have that kind of feature. So this is potassium chloride and sodium chloride, and you see this congruent melting situation. Okay, so basically, depending on the interactions of these things, so the ideal would be like this solid solution. And then if it's non-ideal, it's going to start to deviate like this. So this is a case where the liquid's more stable than the solid solution. If the solid solution is more stable than the liquid, you get the same thing, except that the U points up. So it kind of goes the other way. So then you can start to see that it's going to be like the interactions. So the non-ideal mixing terms are going to be important to what the shape of the phase diagram that comes out. So you can go from something simple like that to something marginally complicated like that, just by messing around with this interaction parameter between the components. So I'll show you. I mean, this is basically from the book, so I'll just show you how you do that. In terms of the free energy curves, so that the liquid is more stable, so the liquid has a lower free energy. So that it would have been kind of parallel to the solid solution curve. Because it's more stable, it droops down. Because it droops down, you get these pinch points that are the the liquid's more stable over this entire range, and you get a pinch point where the solid becomes more stable. Right? And then you have kind of equilibria between the liquid and the solid with a tangent line like that. So that creates this curve. I mean, that free energy plot creates that curve. Went through the different shapes. I mean, this is just showing how the eutectic free energy curves would look. But again, you can create all these curves just by messing around with the Helmholtz interaction parameter, the A12 number, right? So, and he shows how to do that in this chapter. So he says, so he's doing the same thing with making the chemical potentials of the solid and the liquid equal to each other, right? To get the equilibrium points. And then he's got, instead of ideal solution where he had mole fractions, and then mole fractions plus the heat capacity was the last complication. This is saying they're not mole fractions, they're activities. So you have the activity part, the mole fraction part that we already did. There's also this activity part. So he said, like, log of the, so there's a relationship between the activities, the activity coefficients, and the Hildebrandt parameter. So you have there's two activity coefficients, like A and B, for the two components, but they're related to the same Hildebrandt parameter through these cubic equations. Like ln of the activity is the Helmholtz miscibility parameter divided by RT times the other components squared, mole fraction squared. And so we got that a while ago, but basically, so here you have ln of so the chemical potential is ln of X, RT times ln of X, or minus RT ln of X is the chemical potential. And then when you add activity, you have ln of the activity coefficient. You can change ln of activity coefficient to this, just the Hildebrandt parameter, if you know the XA and XB terms, right? So basically, you can translate, so you don't need to worry about two parameters, just have one parameter. So you have three parameters. You have the composition, but they sum to one. So there's only, so XA plus XB is one, so you only need XA. And then you have two activity coefficients, but you only need one because the if you already have the mole fraction, because the mole fraction converts activity coefficient of A or B to the Hildebrandt parameter, which is a single parameter. Well, Hildebrandt parameter is an easier way to look at it. And also you don't have a log because ln of the activity coefficient is the Hildebrandt by RT. So you substitute ln of gamma by omega by RT, then you have the other components mole fraction. So this would be ln of the activity coefficient of the A part, but it's the B mole fraction used because that's how these equations work, right? So anyway, so you end up with the same balance and the same equations, except you have this added term. And if you wanted to, this is ignoring the heat capacity. So if you added in the heat capacity part, you'd have like that term too. You can look that up again. Like you can look up all these things in the NIST webbook to plug them in. So basically, you just have these Hildebrandt parameters that are going to govern the construction of the phase diagram. Right, but it's not exactly gone through totally here because it's just adding things onto things onto things. And this is what the CalFAD program is going to do. So in the end, you just go to CalFAD and use the pull down menus, but it's doing this type thing. It's using a Hildebrandt parameter. Then the book, he does a nice thing. He goes through like every kind of phase diagram using using the Hildebrandt parameters. So if it's an ideal solution, those things are zero, and then it's just the ideal mixing, right? And then that's the thing we did first, where you got the ln of the compositions, and that gives you the phase diagram. So you have two parameters to play around with. The liquid phase, so you have A and B mixing, and then there's an interaction parameter for the liquid, in the liquid phase where they mix, and then the solid solution phase where they mix. So you have two interaction parameters to play around with. So you can say that the thing is, when that interaction parameter is negative, that means that the enthalpy favors mixing. That means A and B likes to be together more than A likes to be with A and B likes to be with B. Right? So this thing's negative, that means you're favoring the liquid phase. Solid solution zero, that means it's an ideal mixing. Right? So when the liquid's more stable, which we saw before, then the Gibbs free energy dips down further. That's the thing we saw. See. So that's here. So the liquid gives free energy because that omega is negative. This thing dips way down in the middle, right? And when it dips way down, you get this kind of crossing point where the solid's stable and the liquid's stable. So you get this solid solution behavior with a dip in the middle, right? So that's this case. We have omega minus 15, and this one's 0. You made the liquid more stable. You get congruent melting. Right, liquid stabilize. And then if they're both 0, you get this simple solid solution behavior. You just have a central gap and you have both things. That's the one that's just the solid solution one. There it is. Here, this one. I guess it doesn't show the free energy curves here, but the free energy curves would just kind of be two hues that are kind of symmetric with each other for that one. And then if you destabilize the liquid, so when that's positive, that means that it favors demixing. So the liquid phase wants to demix and the solid solution is still 0, then you get this upward tilt. And if you looked at we don't have the free energy plot, but basically the free energy for the liquid would have been U, and it becomes like a kind of a flat thing. And the liquid, then the solid solution becomes more stable. So it shifts it up instead of down. So these are like deviations from ideality. This is liquid more stable. So liquid eats up more of the phase space. This is solid more stable. So it eats up more of the liquid. So solid eats up more of the phase space. It's just shifting it up and down from the central one where nothing's more, they're the same stability. They're both ideal. Right, so this is kind of a nice way to look at it. It like explains exactly what's going on in the phase diagrams. And also, so this is the simplest case, right? So, but if you start really messing around with these omegas, then you can get every other kind of phase behavior. So if you say stabilize the liquid, destabilize a solid, then you can get a eutectic behavior. Yeah, in fact, by changing both, you can get eutectic of various kinds. And if you destabilize both, you get this kind of weird, complicated phase behavior, which has a monotectic transition right here. You have liquid and solid goes to solid. That's this C. C is wherever those things are listed. Oops, I guess they're not listed here. Sorry. They're listed below, but here. So monotectic reaction is liquid goes to solid plus liquid. And that's what's going on here. Like you have a liquid phase at the top, it goes to a solid phase at the bottom, and then there's a liquid, another liquid phase that's in equilibrium with. So basically by changing these, you can get every kind of phase behavior they want with just 2 parameters that you're messing around with. So that's like pretty powerful. Like if I said I could go from a solid solution to a eutectic by giving you 2 numbers, you know, that would be hard to believe that you could do that. So let's see. Anyway, so this is from the book. I mean, you can read this part, I guess, but basically, I mean, it should be a little bit of a revelation that you can do that, you know, that you can construct those complicated phase diagrams. So yeah, so this is true. So if you think about this, so you have 2 parameters. So say you wanted to get this phase diagram, like this phase diagram, or even this complicated phase diagram, right? So and you can measure, so you can see like, oh, you can go through an experiment and do temperature quenches and see what phases you get out of it. So how many of those do you need to reconstruct this entire and predict all these little nuances, right? Like how many measurements do you actually need to do that? So each measurement, you're going to get the compositions of the phases and the number of phases, the volume of the phases, and the composition of the phases, like doing TEM or something. So basically, because there's only 2 parameters, you only need to do 2 measurements. Like if you do 2 measurements in this phase diagram, then you can predict the entire phase diagram. Like it's kind of incredible that you can do that. Like it's only 2 unknowns. If you do 2 measurements, that's all you need to reconstruct the entire thing. Because as long as you follow the Hildebrand model to predict it, right? So it's powerful to do that. Like you don't have to measure every possible temperature and every possible composition. You need 2. It's incredible that you can do that. So it's a real show of force that works, Anyway, then I already went through, and we had on this homework, I think, the intermediate phase business, where there's just a magic composition. It's got a super low free energy. It's basically the system clicks together. It's like the bricks click in the right place, and that's the only way. If you shift the bricks a little bit, it falls apart. So you only have one composition, and that acts as if it was another pure component. So the phase diagram is going to be kind of separated as if that was a pure component, right? So and in this case, like this CSC phase diagram, which is calcium zirconia oxide. So it's got a lot of these intermediate phases. You have like one here, one there, one there. And some of them have congruent melting where you go from liquid to solid, and some don't. Some have melting where you go from solid to 2 solid phases, right? So incongruent melting. So anyway, if you're working with phase diagrams, these intermediate phases, like for nickel super alloys and things for jet engine turbines, and these intermediate phases become like the main topic of discussion. And you can see for these kind of superconductor mixed or multi-component oxides, they become important too. So there's a variety of things. If you're studying crystallography, the intermediate phases become like a topic. It's like the main topic. This is another titanium silicon phase diagram, just pretty complicated. Titanium's a transition metal, and silicon isn't, so it complicates the whole situation. Or you can get TiSi and TiSi2. So the titanium would be like +1 or +2. I mean, the different crystals that it forms. So these are some other phase diagrams, just typical. They're just examples, yes. Then this is showing the different kinds of this monotectic phase. So anyway, there's a series of these points where you have no degrees of freedom left. So you have like 3 phases that are at equilibrium with each other. Like the eutectic, you have a liquid and 2 crystal phases. So you have 3 phases that are in equilibrium all with each other at that point, and that becomes an invariant point. It's just a point. It isn't a line or an area. So an azeotrope or vapor to liquid composition is fixed. That's this curve for a liquid, kind of a liquid. Well, there's a liquid solid solution. I guess it's the same as the azeotrope for liquid vapor. Looks like the same thing. So it's a single point. We have a vapor to liquid with the same composition. And then congruent meltings. Congruent melting and azeotrope are the same thing. It's just that in congruent melting, it's solid to liquid. In azeotrope, it's liquid to vapor. And it's liquid to solid, vapor to liquid to fixed compositions. And then paratectic is like 3 solid phases or equilibrium. And then eutectic, you have liquid to 2 solids. Monotectic's liquid to solid plus liquid. So 2 different liquids and a solid. And then syntectic's liquid plus 2 different liquids go to a solid. Right. And basically all those can be found in the various phase diagrams in here. So I don't know. I guess you just need to know the names. You don't actually, it depends on what systems you're working with and whether you'll run into these or not. But eutectic is the one you have to know. That's the one you absolutely have to know, which is the first phase diagram I showed you. It's like this thing. Right, so this you should become pretty familiar with, and everything else. Everything else is kind of an oddball. Like you'll run into it once in a while, maybe, maybe not, you know. So anyway, so this is that business. Tactic, and then this chapter also has a freezing point depression section which differs. So this is the equation he gives. So if you add an impurity, like if you add salt to water, you lower the freezing point. That's how you melt ice with salt, right? So that's kind of an important thing. And also, if you have things that are marginally soluble in a solid like salt and water, then basically it's important to know what the melting point is going to shift to, right? So and you can see that on the phase diagrams and the shifting of the melting point. Like in other words, the 10 is melting at different temperatures here along this curve. So there's some function that describes the melting curve for 10 as you add bismuth to it. Right? Bismuth would be like kind of an impurity in the 10, shifting the melting point. So there's a way to just calculate that. So in the book, he gives this pretty complicated function, like having to do with the activity coefficients of the components. And I couldn't really find a derivation of this, and that it didn't. Anyway, it's a pretty complicated function. There's a traditional thing for ice and water kind of situation, and this is the routine that you go through. So you say dg's VDP minus SDT, and then you say isothermal and ideal. So you get rid of the entropy and you just have the V. Then you put the ln P term, which is ln of the activity. So that's a standard ln activity term. So basically, if you say that if you have a pure component, the activity is 1 and ln of the activity is 0. So that term goes to 0 for the pure component, like pure ice. So B would be pure ice, right? And then at that point, if it's isobaric, then you have minus SDT for the chemical potential for the solid phase or the ice phase. And then you want to equate that chemical potential with the ice and salt phase, which is the solution phase. So you have the same term, SDT, but it's S for the solution. And then you have the activity coefficient of the solution. So in other words, the salt and the water. So ln of the composition of the salt in the water times RT. So it's almost pure water. So this term accounts for the solution, and then you add in the solutes contribution, which is this ln of composition of the salt. And the salt amount is small. So you say that if you expand the exponential minus x is 1 minus x plus x squared over 2 minus x cubed over 3 factorial. But if it's small, then you can just forget about the higher order terms, and it's 1 minus x. Right? So that means that if you take log of both those sides, ln of 1 minus x is minus x. So you have ln of y, so that would become minus y. Like that thing just becomes minus y if y is small. So then you can just, instead of having d ln of y, you have dy in the equation here, which simplifies the whole thing. I mean, you can just kind of get the composition from that. So you plot the y, have delta s dt, and divide by RT, which is a prefactor for y when you said RT ln of the activity. And then you get that expression. So you have a differential equation for dy, which you can integrate. Basically, you'll end up with this. This is delta s, and delta s is delta h over t if delta g is 0 at equilibrium. So between solid and solution are at equilibrium. So you just substitute for delta s, delta h over t, you end up with this t squared term because you already had a 1 over RT here. And you just end up with this function for freezing point depression, which is simple. So it's just gonna freeze. So so T freezing is 0 degrees C for pure water. So then you're just going to add more and more salt. So T freezing is fixed. Delta H of melting at water is fixed. R is fixed. So this is just a linear equation. Like the freezing point should be linear in the composition, and it should decrease as you add more stuff to it. So that's kind of a simple rule. It should just be a linear dependence. So that's that rule. Delta T is linear and Y. The more salt you add, you lower the temperature more. And the slope of that's got to do with the freezing point and the enthalpy of freezing. So his equation is like delta T is this kind of mess. So YA would be XP. So it's also linear in X. And he's got an RT in it, but he's got these weird, he's got the entropy of fusion instead of the enthalpy of fusion. And he's got this 1 minus F minus K. And K is this gamma thing. So this thing's more elaborate. I think I don't know, it's still going to be linear in the composition. So still expect a straight line that goes down. So if you look at like the melting point, so you increase the amount of salt or bismuth in this case, this should be a straight line going down by those equations. And it's actually a little bit of a curve. So the ideal conditions are like at the beginning where it's a straight line. That'll be your salt water kind of melting point depression thing. Right. So anyway, that's in the chapter 2. This is I think this thing you should know that basically the more salt you add, you get a lower temperature. It's proportional. And maybe you should be familiar with that equation because that I think is one of the fundamental thermodynamic things you can see and kind of people it happens to people, you melt the ice with the salt. So it's kind of important. Then there's 2 other things in this chapter that I want to go through. Is that okay with you guys, the salt melting? Have you seen that before? I should have seen it before. I mean, it should be from undergrad, but basically, to me, that's important to know, like, why salt melts ice, and why so you're going to add something, and is the melting point going to rise or drop when you add the other stuff? The answer is it always drops because this equation says it's negative. So it has to drop, and it's going to be at dilute condition when you're like the Henryan regime, not the Raoult. So the dilute regime, it's always going to be linear at the beginning. So if you go like whatever you find, the beginning of this point has to be linear. So it is there. That's kind of how it should be. And it's linear over here too when you dilute the other way. So anyway, and then actually from the slope of that, so you could use that if you wanted. You could say from the slope of that line, you know the composition of the temperature, then you know this whole term. Like so you could use that line slope to determine the enthalpy of melting from that curve if you wanted. If you knew the freezing point would be this 502, whatever. That's a TF. Then your T is this thing going down. So you already know the TF. So the slope of that gives you delta HF. Delta H of the melting for whatever this is, 10. Right? And the slope of this thing over here gives you the delta H of melting for the bismuth, pure bismuth. And delta H is what you need to construct the whole phase diagram also. Or like when you go back and you want to know, I want to reconstruct this phase diagram under an ideal condition, then all I need is the delta H and the freezing point, which you have. So basically from that slope, if you believe that linear equation, you could predict the whole phase diagram just from that slope. Because you wouldn't even need to, you just need like a point here and a point there. But you need the equalators, you need 4 points to do that. But basically, it's possible to do that. You only need 2 to do the whole phase diagram, but 4 would give it to you also. Anyway, that's sad. So that's a trip down rabbit hole number 25 or something. So anyway, I wanted to show you these, which you may have seen before, or may have not seen before. It's a ternary diagram. So you have 3 components that are mixed together. Then you're going to map out something like what are the phases that are present at that composition. So basically you have like A, B, C. So pure A is down here, pure B. So this is like clay. This is a mixture of clay, something else, and sand. I don't know what this one is, but basically it's 3 things that are mixed. In the homework, it's going to be 3 oxides that are mixed. So it'll be like the component. So it can be any three things. So any field is going to use a ternary diagram. So anyway, so the pure clay is going to be up here, like where it's 100, that's pure clay, it's 0 of this thing. And pure, the red thing is over here, and pure sand is over here. So if you go along this line, you have no clay, right? But you have a mixture of sand and whatever the red thing is. Right. And if you go along this line, there's no whatever the red thing is, but you have sand and clay mixed. I say you're making concrete or something. I don't know what you make with sand and clay. But basically, if you go along here, this is just a pure, it doesn't have that component. You go along here, and this doesn't have any sand in it. It's just clay and whatever the red thing is. And if you go exactly in the middle, then you have 30% of each of them. I mean, you have 33%. You have 1/3 of each if you go to the middle. Right. So it looks a little bit like an orientation thing. Like in the middle, you have no. Anyway, so basically the middle is an equal mixture of the three. So you can read off the compositions. Like if you go to a point here and it's 60% clay, and if you read that down, it's 80%. It's let's see, where am I? Lost and lost. 60% clay, and I go to here, and that's 20% of sand. So 60 plus 20 is 80. If I go out to the other one, should be 20% of the other, which it is. You're like 60, 20. So you're right there. Then so they add up 20, 60, and 20 gives you 100. Right. So if you follow the lines and you find a point, you need only 2 compositions to get the other one's composition. Right, so that's one way to read this thing, is to kind of go across the lines. And they're color coded here, so it's kind of easier. But actually, when you get to a point, there's 2 lines, so you don't know which one to take. So anyway, I'm not sure exactly how you tell which one to take, but basically it's easier if they're color coded. So it gets to be a little hard to figure out what's going on, but they should, all the 3 components have to add up to 100. That's the idea of this, right? So I mean, it shows like 3 ways to do this. You can take, if you don't have a grid like that and they aren't color coded, then if you take the normals to this, you can get the compositions. If you take like those 3 lines would add up to 100% line. And if you took the sum of those 3 lines that are the normals, then you would get the so that the red one over the total would give you the composition of red. And then the green over the total gives you composition of green, and the blue over the total gives you composition of blue. That's the idea of that way to read it. So there's several ways to read these. Like, there's this normal way. Does this follow the line way? You need to know which line to pick. And then you can do this kind of from the angle way. I don't know why that's beyond the realm. This thing's showing up. Let's see, let me just escape this. I did get rid of that bar, but I don't think that's exactly possible. Oops. Let's mess this guy up. This guy, I'm way down. Yeah. So if you take the, let's see, so if you find so you have your point and you have the corners. So you can go from the corner to the point. See, this is too small to see though. So this is like a third way to get it. So one way is the normals, one way is read the grid, and the third way is take the corners. If you use these, and you're going to have to know these to figure out what's coming out. Yeah, because a lot of times you just get a ternary diagram like that, and it doesn't say anything about. So you have a point. So what does that mean? You know? So anyway, you go from B to X, or here, right? So see, you go from your point, from your corner through the point out to the other side, and then you get point N. So if you go like NX, so you're going from B, and NX over NB gives you the amount of B in it. percent B. So if it's pure B, it's at that point. And if it's far away from B, it's small. That makes sense. So the small one over the long one gives you the percent B. Right. If you're close to A, then it's got to have a lot of A in it. So the long one, so like MX over MA gives you the amount of A, percent A. It kind of makes sense. I mean, there's probably a way to do this geometrically to figure out how this works. But basically, this is actually the simplest way to figure out what your composition is. So you take your corner where it's 100%, draw a line through it, you get that thing, and then measure that length and this length, and the far one over the close one gives you the percent of that thing, or the fraction of that thing. Anyway, and then you can also do this normal line thing, or you can figure it out from the axes. Problem with the axes, if they aren't color coded, you're at 20%, which line do you take? How do you know to take the one that goes down? So if you're at the blue one, it's not the one that goes down, it's the one that goes horizontal. If you have the green one, it's the one that goes up or something. I mean, like at the green one, you could pick either one, right? So which one is the right one? That's always the problem you run into. So the grids actually don't help that much sometimes. It gives you a 50% chance of being right. And if you take the point and you sum them up and they don't add up to one, you pick the wrong one. I guess that's the main theme of that way. This way is kind of straightforward, but it's a little bit kind of complicated. Right. In other words, well, this way is pretty straightforward. It's just like, well, the blue and the red swapped here, and the green. This way is complicated too. This is the simplest way. You could go from the corner through the point, get there, take the ratio of that to that, and it's the fraction of that guy. And all the fractions should sum up to 100%. Anyway, you don't need to do that for the homework, but there are ternary diagrams to look at. And then what you end up with the ternaries is this kind of thing. So I went to this because this thing chops off the bottom of the PowerPoint. So this is temperature, and this is composition of three components, and they have phase behavior. So there's a single phase region at the top. At the bottom, it separates into different phases, alpha, and then whatever, there's some other phases here. So it's just a generic example. So you end up with a surface. So your phase diagram becomes a surface with a three component system. Then to use that, you do various slices through it. So you're gonna have to, so this is a slice. So this is temperature. So if you do a slice, anyway, they've shown like a couple slices through it. These are isothermal slices, which would be a horizontal slice. And this is a iso something else slice. I'm not sure what they're holding constant here. But basically, and these are temperature lines, isothermal lines on it. All right, so you can do, so the idea of having this ternary diagram is to make this 3D plot, and then you can kind of do slices through it to figure out the behavior of the system. Right, so this will be a little bit more understandable, I guess, when we mess around with it for this homework. This guy, 6, right? So this is like this year paper in Nature, and they're doing ternary diagrams of oxides. So this is an example. So when you make these kind of complicated mixed oxides, like in the paper last week, where they're making a cathode, and he mentions cathodes in here. So you're gonna start, so you can buy certain oxides like boron oxide, barium oxide, and lithium oxide. So you can buy those, and you're gonna put those into like a mill them up, and then maybe heat them up in an oven, a furnace, to some temperature, and then you're gonna hope that they go through some reaction where they swap out the metals, like the transition metal swap. And you hope that that becomes randomized, right? So anyway, so what they've done here is anyway, I'll go through this on Thursday. Basically, they do density functional theory to calculate the energy, like the reaction energy of combining these things. And they plot out on a ternary diagram the energy surface for these, kind of an energy surface, what's going on. And they get through various slices of that to tell so the minimum energy lowest energy is the thing that would happen. So if they say I'm gonna mix B203 with DAO, and then which one, what will result from it, right? So the DFT predicts that it's gonna be that thing. Then they use robots to do that. So I'll go through this next time. I can show you the robots. There's videos of the robots here. So they set up a robot lab to make 250 of these mixed oxide things. The robot does all the work, and they also argue for robots over people in this paper. It's kind of interesting, a little bit shocking. But all right, let's see if it can play this on this. Done. Here, play. This is in Michigan, and they're working with a company. So somehow this robot works all night, doesn't complain, no vacation time, doesn't take Christmas off. Anyway, that's the joy of robots here. But anyway, so this kind of automated lab is like a big deal right now. That's why it's in Nature. Everyone wants to have an automated lab. And they show all the different steps of their process. So this is a picture of the. All right, so I'll go through this next time, but that's why I wanted to go through ternary today. So then we can kind of look at ternary from that. Get rid of this. So that's one thing, ternaries. And the other thing that I wanted to say about phase diagrams is this business. So if you work, so that's working in powders, like they're doing oxide powders, but a lot of times like they're making these mixed oxides from solutions. So they're mixing up salts. So then you have this other kind of phase diagram, which isn't a phase diagram at all. It's called a predominance diagram. So you have like a reaction, chromium oxide with acid makes hydrogen chromate, right? And you can also make dichromic oxide or chromic oxide or hydrogen chromate. There are all three species are present in solution when you put it in an acidic solution. It's like page 5 to 7, right? So you want to know like, well, what species is dominating in that system? So you take the equilibrium constants for the reaction. So that would be like the mole fraction product or mole fractions of the reactants multiplied. Right? So the ratio that gives you the equilibrium constant of it. So you have that for the chromate plus protons, is hydrogen chromate. You have the same thing for hydrogen chromate goes to the dichromate ion and water. And then you have hydrogen and the chromate goes to the dichromate and water. So it's like 3 reactions. There's 3 lines on this. And when your reaction constant is 1, then those things are equal. So you'd have equal hydrogen chromate and chromate. You'd have equal amounts. So when K is 1, so you have hydrogen chromate and chromate, then that's the green line. So if you make K of 1, you find out that the acidity has to be 1 over K1 because there's only one parameter left in the equation. And then basically that's the green line here. You have that pH. That pH is 1 over K1. Of course, log of 1 over K1 would give you that number. And then that doesn't matter. So that would just be, you know, once you get to a higher pH, it makes chromate ion. And then if you go to lower pH, you get hydrogen chromate. But there's still some chromate ion. It's just there's more hydrogen chromate than chromate ion. So across this, they aren't really phase lines, or like predominance lines. Hydrogen chromate predominates here, chromate predominates there. And then the same for the others. They can figure out by saying that the K is, you can figure out basically what the acidity and what these compositions are, and you can map out these lines where you have the predominant ion in the system. That's called a predominance diagram. And if you're doing solution, you can, there's like industrially, you're going to take these powders and mix them together to make these multi-component metals or oxides for battery electrodes and for fuel cells and all this stuff, right? And then, or superconductors, you make the same way, right? So basically, or you can do it from solution. If you do it from solution, you're going to do it, you're going to basically need these predominance diagrams to figure out what you're producing from it. Then you dry that, calcinate it, and make the product from a solution. Right, so anyway, predominance diagrams could come into play depending on what you're doing. And then if you really do that, so there's a whole section here about electrolytes. Like there's a whole kind of science to electrolytes, but I don't go through that usually. Anyway, there's like, here's 100 slides here or something on electrolytes, but I'm not going to go through that. But if you want to learn about electrolytes, there's a bunch of slides here. I can explain them to you if you want. But basically, you probably won't want to. If you get into the work of solution work to make mixed oxides, then you need to figure out a lot, like a book about electrolytes, basically, how they behave. But this is step one of that is a predominance diagram. So if you have that, that's good. All right, so that's everything from the phase stuff. So that's why I wanted to kind of just finish that stuff off before going to the next section. Any questions on any of that business? I just get rid of it. It's gone. The next thing is this phase stability. Oh, let's see. Is there anything? Yeah, there is. Let's see. There's a lot of papers here, like the CalFad program. There's a paper here where they use the CalFad to calculate. I mean, there's a lot of papers where they use CalFad. This one's kind of 2021, so it's kind of recent. They're using CalFad to calculate phase diagrams, basically. It can spit out the free energy, so it can spit out the whole everything you want, but the end product is going to be like this eutectic phase diagram I was getting for silver, copper. And I don't know, that's just an example of a paper where people are using CalFad. There's a lot of phase diagram papers here. I don't know. I stuffed them in here for one reason or another. The CalFad ones, I think I don't know, we did that for homework before. Like we downloaded CalFad and calculated the solder lead 10 phase diagram or something, but anyway, so that, yeah, I guess that's about it for that business. Let's see, that. So we got this phase stability thing. So anyway, this is just a picture. I think this is from our book. So anyway, they're just showing like, what does it mean about phase stability? So basically a stable, they're showing it in terms of gravity, right? So if you have a stable situation, then you have a valley and the ball goes in the valley. If you have an unstable situation, valley falls on top of a mountain, it's going to fall off. And then you can have metastable, or you can have metastable, which means you have this local valley. So you saw that with the free energy diagrams, like there are places where you get stuck. You have barriers to get over. And then the spinodal isn't really a metastable. It's like a point of inflection in the free energy curve. So basically, this kind of is what spinodal is. So spinodal again, let's see. We have a picture of spinodal here somewhere. That would be pretty useful. So here's the Hildebrand equation. You change temperature and the enthalpy term begins to dominate, then you get phase separation. Right. So as you drop the temperature, so chi is 1 over temperature. So as you raise chi or drop temperature, you get a double dip in it, then you get 2 points of equilibria. But on this curve, so those are minima, right? So those would be like the bottom of the hill. So the ball's at the bottom and that's where it's going to go. So that's a stable condition. But if you're right here at the inflection point, that's the spinodal. So basically that's going to define this other line within the two-phase region, where if you go to the left, phases need to grow, they need a nuclei. So you get nucleation and growth in that region. Within the middle of it, you get spinodal decomposition, which is going to be kind of that kind of free energy, like that inflection kind of free energy in this thing. So that's why this shows inflection point is like a spinodal. That's why they're trying to make an analogy to that. It's not a very good analogy, but anyway, they show that. So it's kind of Guess I put it there too. Let's see. So so you can get, I mean, I showed you before that you can get supercooling, right? In other words, let's see. Not this. But, hmm. Let's see. I showed you before this thing. I think I showed you the thing about the water, supercooled water. So you put the water in the freezer. If it has no nuclei in it, then the water can be supercooled below the freezing point. And then if you add nuclei, or if you add a shock that can just somehow bring it together, then it'll just turn into ice. Ice has more volume than water, so it fills it up. And if you put a nuclei in it, it just forms crystals on that because it's just looking for a nuclei to form the second phase. So the plate could be a nuclei or whatever strawberry he puts in it. So you can just crystallize onto it. Right. So it's just going to crystallize once it hits the table. So it's super cooled water. So you can go beyond it's possible to go beyond the melting point and still have super cold. Let's see, get rid of that. So it's possible to have liquid solid, but you can go to a point where the solid should have a lower free energy, but you're actually in the liquid state. So you can overshoot the thing. Right. And that, in fact, that's how you make a glass, basically. Right. So that's why if you have like the solid, this is an entropy curve, but it could be free energy. So you can cool down and then have a point where you have a lower, in other words, you can have a point where you're at a lower free energy for the liquid than for the solid. So the free energy is negative of the entropy. So this is the entropy. So the thing with the higher entropy has a lower free energy, I guess, at a given temperature. The temperature's changing too. But all right, so this guy Kautzman came up with the idea, like you could plot the entropy curve for the liquid and the solid. Then you could find a point. So the normal fusion points, you have a change in entropy on crystallization, would be like that drop. But it's possible to make a supercooled liquid. And you could go down, and then that would be like a point. Eventually, the liquid will cross the solid curve. I mean, you have lower entropy for that's a paradox because the liquid can't have a lower. The liquid has to have more randomness than the solid, so it has to have a higher entropy than the solid. It's not possible for a liquid state to have a lower entropy than solid. If you extrapolate down the liquid curve, it will cross it, and that temperature is called the Kautzman temperature. And this whole thing is called the Kautzman paradox because it predicts that if you can't supercool, you could supercool to a point where the liquid would have a lower entropy than the solid, and something weird would happen, like a paradox would happen. Like it wouldn't necessarily crystallize after that. So the idea was that this is a way to define, like that would be like the glass transition that you measure shifts with the cooling rate. And if you cool it at a very rapid rate, then you could get to this very low temperature, but you couldn't go below that temperature. So that becomes like an absolute glass transition temperature. That's the idea of it. So the Kautzman paradox, otherwise the glass transition is a moving target. So it isn't a real transition. This makes it a real transition because it's an absolute point where you would have a paradoxical situation if you went beyond that. And that has to be the lowest we could possibly make a glass. Right. So anyway, so that's got to do with phase stability. That's like one of the phase stability things is the Kautzman paradox. And you can kind of do the same thing with mechanical testing too. This section also has to do with like the rates of things. So basically the idea that so if you have a melting point, some temperature where something melts, well, there's a range of places where it could crystallize. So if you go to high temperature, the driving force is going to be the delta T from the equilibrium melting point to the temperature where you're crystallizing it. And the bigger that delta T, the bigger the driving force. But as you cool it down to get a bigger, larger and larger delta T, you're also reducing the kinetics. So the lower the temperature you go, the kinetics goes to zero, like it becomes a glass at some point. So it stops moving. So basically, there's a competition between this thermodynamic driving force for crystallization and the kinetics slow down as you cool it down, which also makes the crystallization rate go to zero. So two things, the transport rate goes to zero as you cool it, and the driving force goes to zero as you heat it. And they compete with each other. That means where you actually crystallize at the highest rate is going to be different than the equilibrium melting point. It's going to be like 20 degrees below it for polymers. These are polymers. So basically, you have the equilibrium melting 20 degrees below is where you'd want to crystallize it to get the maximum rate of crystallization. So they're both of them are exponential functions of temperature, but so they kind of have the same shape. One goes up, one goes down. So one would shoot up like that, the other one shoots up like that, or shoots down like that. So when you combine the two to get the crystallization rate, you get that peak. So that can be a question someone asks you, like, why do you get a peak? Why is there an optimum melting point below the equilibrium melting point? And why is it shaped like a peak? That's a kind of a popular topic in materials. You get this bell-shaped curve for the processing conditions. That's one thing. Then actually, let's see. This is in the book. So the Keltzman paradox is like kind of a famous thing. And then in the book, he goes through this mechanical paradox. It's almost the same thing as the Keltzman paradox, where he's saying that so he's got the different moduli, the shear moduli for a material, and he can predict an instability region in it. I have to go through this again, but basically I'll go through this next time, I think. Anyway, I went through this like in the first couple of classes too, that there's like the whole thermodynamics is going to be governed by this kind of fluctuation idea. So the temperature, so you have an average temperature on a material. If you go across it, it's got regions that have a lot of molecular motion and regions with less molecular motion. If you mapped out kind of a temperature map within the material, it would look like that. There's hot spots and cold spots. They're kind of connected in a network, more or less. So if you had a picture of what the temperature looked like in a given material, that's the mapping of it, fluctuations, what it would look like. So blue would be high temperature fluctuations, and the empty would be like cold fluctuations. So to get an average temperature, they have to sum up to the average temperature. Right? And the size scale of that has to do with the transport, the thermal transport in the material, like the decay of that, and then the KT, the actual temperature, decides like how it's spread out. So it's kind of like KT would want to make it uniform, and the transport makes it more localized. So it's kind of a ratio between KT and the transport will give you the spacing of these things. So anyway, let's see. What do I need to do here? It's just showing the phase behavior. There's some pictures of spinel recomposition in here. So basically, like In metals, you can't get this, but because the spacing of these, so basically what happens in spinel decomposition is it's just phase separates along those lines of the thermal, like this thermal mapping just becomes solid. In other words, the fluctuations, the thermal fluctuations become composition fluctuations. And basically that gets frozen in and grows once you get into the central part of the phase diagram, we get spontaneous decomposition. So you just get automatically phase separation without nucleation sites. So it's just going to follow exactly the tracing of that. And then you can see, like this would be in the nucleation growth regime, this is in the spinol regime, and it's doing polymers because the size scale of these fluctuations in metals is like angstroms. The size scale in polymers is microns because they're bigger molecules. They're 100,000 times bigger than a metal. So you get 100,000 times larger fluctuations on it. And then basically the speed of it is much slower because the dynamics of a polymer is much slower than metals. And metals like millisecond or picosecond, in polymers is seconds. So again, it's like 100,000 times slower and 100,000 times bigger than metals. So basically, this idea, the idea of these fluctuations have developed from metals. This whole thing and the strong decomposition idea was developed from metals, but the only place where you can really see it is in polymers. Right, so metallurgy theories like adapted to polymers to predict these kind of structures you can see. And also you see this kind of thing in biological things too, the spinodal, so anything like high molecular weight, low diffusion coefficient materials, and you can observe the spinodal. And in low molecular weight, and then very fast kinetics, and basically you can't see it. That's the idea. This is showing development of the spinodal. So what happens is that as you have these fluctuations, and then you get what they call Ostwald ripening. So the little things are eaten up by the big things to reduce the surface area, and you get a coarsening of that structure that you laid out with the thermal fluctuations over time with spinal decomposition. So I think these are computer simulations showing that, and that you can also get this experimentally with polymers, how the phases grow with time. With polymers, since this distance of these things is going to be like 100 microns, so kind of like 2 human hairs, and the wavelength of light's going to be like basically on that same range. So you can get this pattern. So these patterns are set up because you have thermodynamic driving and diffusion competing against each other. It leads to a preferred separation distance of these things. So even though it looks random, it has like a perfect separation distance between other domains on this thing. So if you shoot a beam of light through it, you get a ring. The ring has to do with that space. 2 pi over that spacing be the Q for that ring. So the Q's the reduced angle, 2 pi over that is the size. It's basically the peak of this is that thermal spacing size. And then as time goes on and it Ostwald ripens, then the ring goes to a higher angle or smaller size, like decays in that way. Right? That's just got to do with the Ostwald ripening of the initial spinodal phase separation. So I'll leave it there. So next time I'm going to go through the homework, and then maybe I'll do some more of this non-equilibrium things. And then it's quite a bit in this chapter. Anyway, that's about it for today. So any questions, anything? All right, so there's another homework coming up.